In section 2.1, we explore early ideas in atomic theory, and in particular, we're going to review Dalton's atomic theory. These are ideas that should be familiar from Chemistry 139. So, in modern chemistry, we take an atomistic view of matter. That is, we think of matter, or objects, as being composed of particles that are called atoms, and that these atoms are indivisible by either physical or chemical methods. The early known written records we have of these kinds of atomic theories date back to the ancient Greeks, and in particular a guy called Democritus. It's important to recognize that these ideas were not scientific theories, as they were not supported by physical evidence. The first modern atomic theory was written down by John Dalton in about 1808. There's different ways that this is phrased, but effectively, it's built up around 5 key ideas. First of all, Dalton said that all matter is composed of tiny indivisible particles called atoms, so he's just confirming the atomic model of matter. He then goes on to explain that atoms of one type are the same as each other and different from other types of atoms. That is, every atom is unique. Right? Every type of atom is unique. A hydrogen atom is different from a nitrogen atom, for example, but all hydrogen atoms are identical to each other. He further elaborates that the number and arrangement of atom types in a pure substance are what determines its identity. So we're saying how many of each atom type and also the ways in which those atoms are connected to one another determines the identity of a pure substance, that is, of a compound or an element. According to Dalton's atomic theory, chemical change involves a rearrangement in the way that atoms are connected to one another, that is, how they're joined to one another, or how they, or in a chemical change, perhaps they are separated from one another, but there's some kind of rearrangement in a chemical change in the way that the atoms are joined to each other. And his final point is really a statement of the law of conservation of matter. It says that atoms cannot be created, destroyed, or transformed in a chemical reaction. So that last point is important because it destroys the possibility of something like alchemical change. So how Dalton came up with this atomic theory was based on experiments involving the masses of elements in compounds. And in particular, there were 2 key ideas or 2 data points that Dalton had when developing his theory. The first was the law of definite proportions. And so it had been observed that in a pure compound, the elements are always present in the same definite proportion by mass. So for example, if I was to take 2 samples of ammonia and decompose them into the elements nitrogen and hydrogen and get the following data. So sample 1, I get a 1.84 grams total of ammonia, which I can break down into 1.5 grams of nitrogen and 0.33 grams of hydrogen. And then in sample 2, I have 2 grams of ammonia, which I can break down into 1.64 grams of nitrogen and 0.36 grams of hydrogen. Now, when I take the ratio of the mass of nitrogen to the mass of hydrogen, I get, to the last significant figure at least, the same number in each case. So this is a good example of the law of definite composition. It doesn't matter the size of my sample, the fact that these guys were a little bit different. When I take the ratio of the component elements, I always get the same number. And that's because for a compound, that the atom types are always present there in the same ratio. So that's how Dalton interpreted this data. He said that compounds always have a fixed whole number ratio of atom types. It has to be a whole number ratio because, well, an atom is the smallest unit of matter, and atoms are always going to be present in whole numbers because they can't be divided. So for example, water is always going to have the formula H2O. If it doesn't, it's not water. Ammonia will always have the formula NH3. Again, if it doesn't, it's not ammonia. Methane is always going to be CH4, and salt will always be NaCl, and any other ratio of the atom's types indicates another compound. The other piece of data that Dalton had when he was putting together his atomic theory was the law of multiple proportions, and that states that when two elements react to form more than one compound, a fixed mass of one element will react with masses of the other element in a ratio of small whole numbers. So that's a little bit of a mouthful, but let's break it down and have a look at an example. So if I have 1 gram of copper, I will find that it reacts with 0.588 grams of chlorine to form a green compound. If I have 1 gram of copper, I can react it with 1.16 grams of chlorine to form a brown compound. So I have a fixed mass of one element, and then I'm reacting with different masses of a second element. And what I find is when I take the ratio of the masses of the second element that forms stable compounds with my first element, I get a whole number. So what this indicates is that our copper is reacting with whole numbers of atoms of chlorine to form different compounds. In our second compound, we're reacting with twice as much chlorine as our first compound. So Dalton interpreted this that, atoms combine in simple whole number ratios. We don't really know what these compounds are without more data, but perhaps one of them is copper reacting with 1 chlorine, and the other one might be copper reacting with 2 chlorines. So Dalton sees this as meaning different compounds have different whole number ratios of atom types. For example, water is formed when hydrogen and oxygen react in a 2-to-1 ratio, but that's different from hydrogen peroxide, H2O2, which forms when hydrogen and oxygen react in a 2-to-2 or 1-to-1 ratio. Ammonia is formed when nitrogen reacts with hydrogen in a 1-to-3 ratio, but that's a different compound from hydrazine, which forms when nitrogen and hydrogen react in a 2-to-4 ratio or a 1-to-2 ratio. Methane forms when carbon and hydrogen react in a 1-to-4 ratio, and methane is a different compound from propane, which forms when carbon and hydrogen react in a 3-to-8 ratio. So what we're really saying is different compounds have different whole number ratios of atom types. So let's look at some problems from OpenStax illustrating some of these ideas. It says, in the following drawing, the green spheres represent atoms of a certain element. The purple spheres represent atoms of another element. If the spheres of different elements touch, they are part of a single unit of a compound. The following chemical change represented by these spheres may violate one of the ideas of Dalton's atomic theory. Which one? And I hope that what you can see pretty quickly is that in the starting materials we only have one of the green elements, but in the products of the reaction we have 2. So clearly we've got an issue here with the law of conservation of matter, and so the idea that's being violated here is that atoms cannot be created during chemical change, right? That's the problem, isn't it? In a chemical change, all we do is reorganize how the atoms are bound to one another, but in this case, we've created a green atom out of nothingness. Okay, let's see if the answer key for OpenStax agrees with us. The starting materials consist of 1 green sphere and 2 purple spheres. The products consist of 2 green spheres and 2 purple spheres. This violates Dalton's postulate that atoms are not created during a chemical change but merely redistributed. So we were correct. Okay, let's have a look at another one. It says, identify the postulate of Dalton's theory that is violated by the following observations. Now, you don't have to be perfect here and give a number and the exact text. You just have to kind of give the idea. So it says 59.95% of one sample of titanium dioxide is titanium. 60.1% of a different sample of titanium dioxide is titanium. So this is indicating that in these 2 samples of titanium dioxide, you have a different proportion of titanium versus oxygen in each of the samples. So that's not correct. So this violates the idea that compounds have a definite proportion of atom types. Okay. What characterizes a compound is the number and type of atoms that are present in it, and also the way that these atoms are connected to one another. The fact that we've got two different numbers here for the proportion of titanium indicates that something is amiss. So the OpenStax answer reads, the statement violates Dalton's fourth postulate. In a given compound, the number of atoms of each type, and thus also the percentage, always have the same ratio. So I kind of said the same thing without mentioning that it was the fourth postulate or anything like that, because people sometimes list these in different orders. But yeah, we got the idea across. Okay, so this problem here is dealing with the law of definite proportions and the law of multiple proportions. So it says samples of compounds X, Y, and Z are analyzed with the results shown here. So all of them are observed to be a clear, colorless liquid with a strong odor. So the physical description is not helping us distinguish these from each other. And then we find that they are composed of carbon and hydrogen, but each sample has a different mass of carbon in it and a different mass of hydrogen in it. Okay, so then we are asked, do these data provide examples of the law of definite proportions, the law of multiple proportions, neither or both? What do these data tell you about compounds X, Y, and Z? So the first thing that I'm going to go through and do is I'm going to calculate in each case the ratio of carbon to hydrogen. So for X, I'm going to put 1.776 divide 0.148, and that tells me that I get 12 carbons for every hydrogen. For Y, I'm going to do the same thing, 1.974 divide 0.329, and I get 6. And then for Z, I'm going to do the same. You got 7.812 divide 0.651, and I get 12. So we can see that X and Z have the same proportion of carbon to hydrogen in each case. So this is an example of the law of definite proportions, right? So X and Z are possibly the same compound, and this is an example of the law of definite proportions. Okay. Now, Y appears to be a different compound from X and Z. So let me just kind of create a little space here. Let's see if I can make this happen. Y is a different, and we can be certain about this, compound to X and Z, and that's because of the law of multiple proportions. Okay, a different ratio of the atom types indicates that it must be a different compound. So it's a little tricky to kind of get the answer for that one. Now, we can't say that X and Z are definitely the same compound without a bit more information. That we can only tell that they have the same ratio of atom types. We don't know anything about how the order or the pattern in which those atoms are connected to one another. Okay, so that concludes section 2.1, which summarizes early ideas in atomic theory, and in particular what we did was review Dalton's atomic theory.